relative velocity concept. It also can be considered as application of subtraction of vectors. Normally, when we say the actual velocity of a body, we mean velocity of the body with respect to a stationary observer on the earth. A coordinate system which is fixed with respect to an observer on the earth who is at rest with respect to the earth is called as the laboratory coordinate system. Of course, later in Newton's laws of motion, we discuss about types of frames of reference or different types of coordinate systems. But at present, you remember this way, whenever I say actual velocity of a body, it means it is the velocity of the body with respect to the stationary observer on the earth at the given place. So velocity of the body as seen with respect to another body, we call relative velocity. Suppose if there are two ships A and B moving in different lines which are not parallel, then the relative velocity of ship A with respect to the ship B means it is the velocity of the ship A as observed by an observer in the second ship B. Now we are going to discuss the graphical method for finding the relative velocity of one body with respect to another body. Let A be the position of one particle. Let A be the position of one particle and B be the position of another particle at a particular instant. Let O be the origin of the fixed coordinate system, or O represent the position of a stationary observer on the earth who is at rest with respect to the earth. So the direct line segment OA bar is called position vector of the first particle A. The direct line segment OB bar is called position vector of second particle B. The position vector of the first particle A are denoted by RA bar. The position vector of the second particle B are denoted by RB bar. So from triangle law of vector addition, we can write OA bar plus AB bar equal to OB bar. So AB bar can be written as OB bar minus OA bar. So OB bar represents the position vector of the second particle B denoted by RB bar. OA bar represents the position vector of the first particle A denoted by RA bar. So AB bar represents position vector of the second particle B with respect to the first particle A. Suppose if we change the origin of the coordinate system to the point A, or you can choose, if you consider another new coordinate system with origin at the point A, then AB bar will be the position vector of B with respect to A as origin. Now, if you differentiate this, both sides with respect to time t, so d by dt of AB bar can be written as drb bar by dt minus dra bar by dt. Of course, later we are going to discuss in kinematics also about the terms average velocity and instantaneous velocity, but still some of you may be familiar with those terms in the lower school classes and also in the junior intermediate classes. Now, rate of change of position vector with respect to time t. This is the instantaneous velocity vector. So drb bar by dt gives the rate of change of position vector of the second particle P with respect to origin O. That gives the actual velocity of the particle B. Similarly, dra bar by dt, that is the rate of change of position vector of the first particle A with respect to the time t. This is actual loss of body A. So VA bar represents the actual loss of the first particle A, and VB bar represents the actual loss of the second particle B. Means VA bar is the velocity of the first particle A with respect to the fixed origin O. VB bar is the velocity of the second particle B with respect to the fixed origin O. The left hand side, d by dt of AB bar gives the rate of change of position of the particle B relative to the particle A. That gives you the relative velocity of the particle B with respect to the particle A. So mathematically, relative velocity of the particle B with respect to the particle A denoted by V bar subscript B comma A, or sometimes V bar subscript BA. That is equal to vector difference of the actual loss of the particle B and the actual loss of the particle A. So relative velocity of the particle B with respect to the particle A is equal to the vector difference of actual loss of the particle B and the actual loss of the particle A. So actual loss of the particle A means it is the velocity of the particle A with respect to stationary observer on the earth. PB bar is actual loss of the particle B means it is the velocity of the particle B with respect to stationary observer on the ground, or stationary observer on the earth at the given place. Next, I am going to discuss the graphical method for finding the relative velocity of one body A with respect to another body B, which is the almost repetition of the same graphical method which I discussed in the past for finding the vector difference of two vectors A bar and B bar. Now I am going to discuss the graphical method for finding the relative velocity of one body A with respect to another body B. And we follow this graphical method in good number of problems on relative velocity. Same graphical method I have discussed in the past for finding the difference of two vectors A bar and B bar. The only difference is now instead of A bar, we have VA bar. In place of B bar, you have VB bar. Let us suppose the velocity of one body A, denoted by VA bar, represented graphically by the direct line segment OA bar. Let VB bar represent actual velocity of another body B. Means velocity of the body B with respect to the stationary observer on the ground, which is represented graphically by the direct line segment OB bar. The theta denote the angle between the two velocity vectors VA bar and VB bar. So in the figure, OA bar represents the actual velocity of the body A. OB bar represents the actual velocity of the body B. Theta is the angle between the two velocity vectors. Theta is the angle between the two velocity vectors VA bar and VB bar. So relative velocity of the body A with respect to body B. WRT means with respect to, denoted by V bar subscript A comma B. That can be written as vector difference of VA bar and VB bar. As I discussed in the past, that in general, if A bar and B bar are two vectors, the vector difference A bar minus B bar defined as the vector sum of A bar and minus B bar. The same way here, the vector difference VA bar minus VB bar can be written as the vector sum of VA bar and minus VB bar. From definition of negative vector, the vector minus VB bar will have the same magnitude as the vector VB bar, but acts in the opposite direction. That means in the diagram, the vector minus VB bar is represented by the direct line segment OB1 bar. The angle AOB1 means the angle between the vectors VA bar and minus VB bar will be equal to 180 degrees minus theta. Here theta is the angle between the vectors VA bar and VB bar. So the velocity vector VA bar is represented by the direct line segment OA bar. The vector minus VB bar is represented by the direct line segment OB1 bar. So we can substitute VA bar equal to OA bar and vector minus VB bar equal to OB1 bar. So relative velocity of the body A with respect to the body B is the vector sum of OA bar and OB1 bar, which you can find by completing the parallelogram with OA and OB1 as adjacent sides. So OA DB1 is a parallelogram. OA DB1 is a parallelogram. So from parallelogram law of vector addition, the vector sum of OA bar and OB1 bar will be equal to the vector OD bar. Since OA DB1 is a parallelogram. That means OD bar represents the relative velocity of the body A with respect to the body B. And to find the magnitude of relative velocity, you can use the same formula which I discussed in the past for magnitude of vector difference of two vectors. The magnitude of vector difference of two vectors A bar and B bar is given by, as I discussed in the past, mod of A bar minus B bar is given by root of A square plus B square minus 2AB cos theta. Theta is the angle between two vectors A bar and B bar. Same equation can be used for finding the magnitude of relative velocity of one body A with respect to another body B. So using the formula which I have discussed in the past for magnitude of vector difference of two vectors, you can write magnitude of VA bar minus BB bar. It means magnitude of relative velocity of A with respect to B. Of course, that will be same as magnitude of relative velocity of B with respect to A. Because in general, if A bar and B bar are two unequal vectors, then vector difference A bar minus B bar can be written as negative of vector difference B bar minus A bar. That means modulus of vector B bar minus A bar can be written as same as modulus of vector A bar minus B bar. But directions are opposite. That means the relative velocity of B with respect to A will be negative of relative velocity of A with respect to B. That means relative velocity of B with respect to A will have same magnitude but opposite in direction to the relative velocity of A with respect to B, which will be equal to root of VA square plus VB square plus 2VA VB cos 180 degrees minus theta. If theta is the angle between the two velocity vectors VA bar and VB bar, as I discussed before, then angle between the vectors VA bar and minus VB bar will be equal to 180 degrees minus theta. Or you can write as VA under root of VA square plus VB square minus 2VA VB cos theta. So in this equation, theta is the angle between the two velocity vectors VA bar and VB bar. So I am going to consider some special cases in the relative velocity. These special cases we have actually discussed earlier in subtraction of vectors. Suppose if the two bodies A and B are moving in the same direction. Suppose the two bodies A and B are moving in the same direction, then the angle theta between the two velocity vectors VA bar and VB bar will be equal to 0 degrees. So if you substitute theta equal to 0 degrees, you get mod of VA bar minus VB bar. Mod of VA bar minus VB bar equal to under root of VA square plus VB square minus 2VA VB cos 0 degrees. So cos 0 degrees equal to 1. So this you can write under root of VA minus VB whole square. Or you may also write under root of VB minus VA whole square. But remember that modulus of vector cannot be negative. Difference of two vectors again a vector. And modulus of any vector cannot be negative. So modulus of vector difference VA bar minus VB bar will be positive. Therefore, the modulus of VA bar minus VB bar, we write it as VA minus VB. If VA is greater than VB, modulus of VA bar minus VB bar, we write it as VB minus VA if VB is greater than VA. That means in general, if two bodies are moving in the same direction, then magnitude of relative velocity of one body with respect to another body will be equal to the ordinary difference in the magnitudes of the velocities of the two bodies. Suppose if the two bodies A and B are moving in opposite directions, then the angle theta between the two velocity vectors VA bar and VB bar will be 180 degrees. In that case, mod of VA bar minus VB bar equal root of VA square plus VB square minus 2VA VB cos theta. And substitute here theta equal to 180 degrees. So the value of cos 180 degrees equal to minus 1. So you get under root of VA square plus VB square plus 2VA VB, which you may also write as under root of VA plus VB whole square. That means the two bodies A and B are moving in opposite directions. The magnitude of relative velocity of one body A with respect to another body B will be equal to the ordinary sum of the magnitudes of the velocities of the two bodies. Suppose if the two bodies A and B are moving in perpendicular directions, then angle theta between the two velocity vectors VA bar and VB bar will be 90 degrees. In that case, modulus of VA bar minus VB bar equal to root of VA square plus VB square minus 2VA VB cos 90 degrees. You can substitute theta equal to 90 degrees general formula. The cos 90 degrees equal to 0. So you get root of VA square plus VB square. Coming to the fourth special case, as I discussed in the past in subtraction vectors, you can see the special case 4 in subtraction vectors. If modulus of vector A bar is same as modulus of vector B bar, then mod of A bar minus B bar is given by 2A sine theta by 2. The same result can be used even in some of the problems in relative velocity. When the two bodies A and B move with equal speeds but in different directions. That means magnitude of velocity of A is same as magnitude of velocity of B, and magnitude of velocity of each body is suppose equal to V. But the two bodies are moving in different directions, such that the velocity of A makes an angle theta with the velocity of B. Then magnitude of relative velocity of A with respect to B will be equal to, using this result on the left side, you can write it as 2V sine theta by 2. Once again revise the discussion I have done for relative velocity. So in case those who are interested write the note, they can take the notes from here onwards for relative velocity. That means if they need time to copy, they can take a pause wherever required. If VA bar and VB bar denote the actual velocities of two bodies A and B with respect to the stationary observer on the ground, then which are graphically represented so we can once again look at the diagram here. The direct line segment OA bar represents the actual loss of body A. The direct line segment OB bar represents the actual loss of the body B. So if VA bar and VB bar denote the actual velocities of two bodies A and B with respect to stationary observer on the ground, which are represented graphically as indicated in the figure, and the relative velocity of the body A with respect to the body B is given by VA bar minus VB bar. So in this figure, VA bar is represented by OA bar, VB bar is represented by OB bar, and vector minus VB bar is represented by OB1 bar. So relative velocity of the body A with respect to the body B, the vector sum of VA bar and minus VB bar. That means it is the vector sum of the two vectors OA bar and OB1 bar, which is represented by OD bar. In the figure, theta is the angle between the two vectors VA bar and VB bar. 180 degrees minus theta is the angle between the vectors VA bar and minus VB bar. Modulus of vector minus VB bar is same as modulus of vector VB bar, which is written as VB without the bar symbol. So magnitude of the vector sum are resultant of VA bar and minus VB bar is given by mod of VA bar minus VB bar equal to root of VA square plus VB square plus 2VA VB cos 180 minus theta. You can write cos 180 minus theta as minus cos theta. Here theta is the angle between the two velocity vectors VA bar and VB bar. Looking at the special cases, if theta is 0 degrees, then you get mod of VA bar minus VB bar equal to VA minus VB. If VA is greater than VB, that means if two bodies are moving in the same direction, then the magnitude of the relative velocity of one body with respect to other body will be equal to the ordinary difference of the magnitudes of the velocities of the two bodies. The two bodies are moving in opposite directions. Then angle theta between the two vectors VA bar and VB bar is 180 degrees. In that case, you get mod of VA bar minus VB bar equal to VA plus VB. That means mod of VA bar minus VB bar equal to modulus of VA bar plus modulus of VB bar. So if two bodies are moving in opposite directions, then the magnitude of relative velocity of one body with respect to other body will be equal to the ordinary sum of the magnitudes of the velocities of the two bodies. Coming to the case 3, suppose the two bodies A and B are moving in perpendicular directions. If the two bodies A and B are moving in mutually perpendicular directions, then the angle theta between the velocity of A and velocity of B will be 90 degrees. In that case, magnitude of VA bar minus VB bar will be equal to root of VA square plus VB square. That means magnitude of relative velocity of one body A with respect to other body B will be equal to square root of VA square plus VB square. Coming to the special case 4, suppose the two bodies A and B are moving with same magnitude of velocity or same speed V, but different directions, such that the velocity of A makes an angle theta with the direction of the velocity of B. Then magnitude of relative velocity of A with respect to B will be equal to 2V sine theta by 2. Then I would like to go for problems in relative velocity. I will be discussing the first problem. First, I will show you the first problem which I will be discussing immediately. Later, I will show you some more problems for practice. See the problem number 1 in relative velocity. One body capital A is moving towards east with a velocity of 10 meters per second, and another body capital B is moving with a velocity of 10 root 3 meters per second in the direction 30 degrees south of east in the horizontal plane. Find the magnitude and direction of the relative velocity. I'm giving two parts of the problem. First part of the body capital A with respect to the body capital B. Second part of the problem B of the body B with respect to the body capital A. Come on. You can start trying the problem if you are interested to try it yourself. If you are interested to try the problem yourself first, you can take a pause and try the problem. Otherwise, we will look at the solution of the problem which I am going to discuss now. So in this problem, you are given the velocity of A at 10 meters per second towards east. The velocity of B is 10 root 3 meters per second in the direction 30 degrees south of east. So we can choose the horizontal direction towards east as the positive direction of x-axis, and the horizontal direction towards north as the positive direction of y-axis. So horizontal direction towards south will be the negative direction of y-axis. So the velocity of A is 10 meters per second towards east. That means velocity of A is directed along x-axis. So therefore, the component of velocity of A along y-axis will be 0. The velocity of B has a magnitude of 10 root 3 meter per second. It makes 30 degrees with east direction and inclined towards south. So let V bar denote the velocity vector of B, which makes an angle of 30 degrees with east direction inclined towards south. So you can resolve the velocity vector of B into rectangular components parallel to x and y axis. The magnitude of the component along x-axis will be VB cos 30 degrees. The magnitude of the component in the y direction, I mean towards south, will be VB. The magnitude of the component towards east will be VB cos 30 degrees, and magnitude of velocity, I mean magnitude of the component of velocity of B towards south will be VB sin 30 degrees. So, but the component towards south means it is directed in the negative direction of y-axis. The component towards east is directed in the positive direction of x-axis. So, in vector form, the velocity of B can be written as VB cos 30 degrees into I cap, because the component in the y direction has magnitude VB sin 30 degrees but is directed in negative y direction of y-axis. So you can write minus j cap. I cap is unit vector along positive x-axis and j cap is unit vector along positive y-axis. Minus j cap is the unit vector in the negative direction of axis. VB represents magnitude of velocity of B, that is 10 root 3 meter per second. Cos 30 degrees is equal to root 3 by 2. Sin 30 degrees is 1 by 2. So in vector form, velocity of B can be written as 15 I cap minus 5 root 3 j cap meter per second. And velocity of A in vector form, you can write 10 I cap meter per second. It has no component in the y-axis. So relative velocity of A with respect to B, denote V bar subscript A comma B, means relative velocity of A with respect to B. The vector difference of VA bar and VB bar. Can write VA bar equal to 10 I cap, VB bar equal to 15 I cap minus 5 root 3 j cap. All velocities in meter per second. So you get relative velocity of A with respect to B as minus 5 I cap plus 5 root 3 j cap meter per second. So relative velocity of A with respect to B has a rectangular component of magnitude 5 meter per second towards negative x-axis, means towards west. And a rectangular component of magnitude 5 root 3 meter per second along positive axis. So you can draw a separate figure showing the components of the velocity of A with respect to B. So you can start copying the solution of the problem. Of course, one more line you have to write. the solution. So first you finish writing up to this step. For time to copy the solution of the problem, you can take a pause. Take a pause and take your time to copy the solution of the problem up to this step. So once you finish copying, then I will continue the discussion about the problem. So the relative velocity of A with respect to B has a rectangular component of magnitude 5 meter per second towards negative x-axis, means towards west. I draw a separate figure showing the rectangular components of relative velocity of relative velocity of A with respect to B, and it has rectangular component of magnitude 5 root 3 meter per second towards positive axis. That means towards north, like this. So if you write mod of this velocity, magnitude of velocity of A with respect to B will be root of 5 square plus 5 root 3 whole square meter per second. Simplify that, you get 10 meter per second. To know the direction, you can draw a figure here showing the component of velocity. The y component of relative velocity has a magnitude of 5 root 3 meter per second, directed in the positive axis towards north. Again, I am showing this component again here. The x component of relative velocity has a magnitude of 5 meter per second, directed towards west. So these are the two rectangles. This is the y component, this is x component. Show the directions and magnitudes. If you complete the rectangle by representing the two rectangular components of the vector by the adjacent sides, from parallelogram vector, the diagonal represents the vector. So this vector is represent the velocity, relative velocity of A with respect to B, which makes some angle denoted by, suppose, alpha with north direction. Rectangle opposite sides are equal. Therefore, tan alpha you can write 5 meter per second by 5 root 3 meter per second, or tan alpha you get 1 by root 3. So you get alpha 30 degrees. That means you can write the answer in this way: 10 meter per second in the direction 30 degrees west of north. That means relative velocity of A with respect to B is 10 meter per second in the direction 30 degrees west of north. So when we say 30 degrees west of north, means it makes 30 degrees with north direction, inclined towards west. So that is a relative velocity of A with respect to B. The part B of the question, you are asked to find relative velocity of B with respect to A. The relative velocity of B with respect to A will be equal to VB bar minus VA bar, which will be opposite to VA bar minus VB bar. So will be opposite to this. From that you can make out the answer yourself.